Good morning. It's great to welcome you to this pre-recorded Saturday morning physics lecture. I'm Tim Chupp, longtime host and organizer of Saturday Morning Physics. And before I introduce today's speaker, let me remind you that our speaker will answer your questions after the lecture. So please email those questions to physics@umich.edu. It's my pleasure to introduce today's lecturer, Professor Fred Adams, Tao Yu Wu Collegiate Professor of Physics here at the University of Michigan. Professor Adams is a theoretical astrophysicist who has helped illuminate a broad range of phenomena from star and solar system formation to the origin of the universe. He has been at Michigan since 1991 and came here from the Harvard-Smithsonian Center for Astrophysics. And before that, he received his PhD from Berkeley. And he was an undergrad at Iowa State. Fred has received numerous awards for his work in astrophysics, including the Robert J. Trumpler Award and the Helen B. Warner Award from the American Astrophysical Society. And at U of M, he has received the Faculty Recognition Award, and he has also been recognized for his work in the classroom with an Excellence in Education Award twice. In addition to his tremendous scholarly output, over 200 papers authored and co-authored, he has written popular books and treatises, including The 5 Ages of the Universe with Greg Laughlin. So we're really looking forward to Fred's lecture on the degree of fine-tuning in our universe and others. Fred?
Well, thank you, Tim, and thank you all for tuning in today. Today I'm going to talk to you about a big picture question, namely the fine-tuning of the universe. Now let's jump right into it. Let me just put down on the table 3 facts. The first is that we live in a universe that has laws of physics, and the laws of physics allow us to have life develop. In other words, we're here, okay? Now, that raises a small question. If you change the laws of physics just a little bit, could it be that those small changes would render the universe lifeless? Now, this question becomes urgent, or more urgent, in that it's possible, as we'll talk about in a minute, that other universes could actually exist. And not only could other universes exist, and I'll tell you what I mean by that, it's possible for those other universes to have different versions of the laws of physics. So all of these considerations pose the question that we want to address in today's lecture, namely, is our universe fine-tuned for the development of life? And if so, how much? So the first question that you need to wrap your head around is, what does it mean for there to be another universe? Well, let's start by saying, well, what does it mean for us to be in a universe? Well, we've heard many lectures about the Big Bang and Big Bang theory during Saturday morning physics over the years. And the basic idea is that our universe started as this little tiny expanding piece of space-time that gets bigger and bigger as time evolves. So we live in this great big bubble shown here, which is our universe. It's an expanding space-time that's broadly coherent. Now, the part of the universe that we can actually see is a tiny subset of it, which is labeled here as our observable universe. So there's different hierarchies that we can see. We can see our observable universe, but our observable universe belongs to a bigger region of space-time, which is still our universe. But it's possible for there to be other Big Bang events and the launch of other expanding spacetimes, and those other expanding spacetimes we can rightfully call other universes. So there could be other regions of spacetime, and that's all that we mean by having other universes. But there's more. In fundamental theories like string theory, M theory, and their generalizations, it's possible for there to be different versions of the laws of physics. Now, this is not a lecture on string theory, so I won't go into the details, but the basic idea is that when the universe is hot and young, it can settle down, and then it cools down, it can settle down into different vacuum states. And what we mean by that is that the configuration that sets what it means for empty space to be empty space can be different from one case to another. And in the present context, if you go back to the previous slide, where we have more than one universe, and we have this transition from high energy to a vacuum state, the different regions in this picture can have different vacuum states in this picture, thereby leading to a collection of different universes. And this collection of different universes can, at least in principle, have different versions of the laws of physics. And then we can ask the question, given that we can have different universes with different laws of physics, what do we need for the laws of physics to allow for life to develop? That's the million-dollar question that we want to address. Now, along with that, there's actually another interesting possibility that I'd like you guys to keep in mind as we talk today, and namely that when we look at our universe, we are in it, it's well suited to us, or more precisely, we are well suited to it. But suppose you were going to start designing a universe from scratch. Could you, at least in principle, could you define a better universe? Can we do better? Do we live in the best of all possible universes? Or can we make a designer universe that's even more friendly to life than our own? I want you to hold that thought, and we'll come back to it at the end of the talk. Now, before we jump into this, let me just come clean and remark that this, in fact, does represent a counterfactual exercise. What I mean by that is we're positing or thinking about or considering other universes other than our own, and by definition, we live in our universe, not these others, so there's a certain problem in trying to experimentally verify this. Nonetheless, some people take this idea of a multiverse seriously, so it makes sense for us to ask, could they in principle develop life? There's also a parallel development called the anthropic cosmological principle. This principle says something along the lines of, well, we don't know why we have the laws of physics that we do, but we would like to know why we have the laws of physics that we do. So if we can make an argument that says, well, if the laws of physics didn't have this certain form, we wouldn't be here to ask the question, therefore, the laws of physics must have that form, at least for our universe. So the point is that these anthropic arguments give you a partial explanation for why the laws of physics have the form that they do. Now, to be clear, if we had a more fundamental argument and a more fundamental understanding of why the laws of physics took the form they did, they would throw out the anthropic arguments in a moment. But we do not have such a thing now, and they are used. But in order for the anthropic arguments to make any sense, it has to be the case that only a small subset of universes would allow for life. Otherwise, the arguments don't have any predictive power. And the final reason to consider these kinds of counterfactual exercises is the following. By looking at other universes with other laws of physics, other possibilities, ultimately we gain some understanding about how our own universe works. And as an astrophysicist, that is our goal. We want to understand how our universe works. So one of the basic ideas of this exercise is simply to turn the knobs on the universe until it breaks. And by understanding those limits, we understand how it is that our universe works to a bigger degree. So with all of this introductory material, let's jump into the actual problem and see what we're actually going to talk about. So the first order of business is to ask, what parameters could you imagine varying from universe to universe? In other words, what does it mean when I say that the laws of physics could vary? Now, right away, we have a problem in that nobody agrees to the answer to this question, but that won't stop us. We will just continue on. And let me try to give you a little more detail. The first thing is that there are two separate approaches, okay? If you're a hardcore fundamentalist particle physics person, then the thing that matters is the standard model of particle physics, because you're doing the ultimate reductionist exercise and breaking everything down into as smallest possible constituent parts. From that point of view, the parameters that matter are the 26 parameters of the standard model of particle physics. These parameters include things like the masses of the quarks, the masses of the leptons, in other words, the masses of the fundamental particles, the masses of the force-carrying particles, the strengths of the forces, the coupling constants, some mixing angles, and a number of other things. But the problem here is twofold. One is there's 26 of them, and not all of them really matter that much. Some matter a lot. And the others is that when you actually look at the things in our universe, like a star, there's not a knob in the stellar structure theory that says, well, I'll use the mass of the top quark It doesn't appear in the stellar structure equations. What appears instead are composite-derived parameters that will fundamentally depend on the fundamental parameters, but we don't actually know exactly the transition. A good example of that is that there's different nuclear reaction cross-sections that set how stars work. That makes sense. And of course, ultimately, the nuclear reaction cross-sections depend on the strength of the strong force and the strength of the weak force and the strength of the electric force, which keeps the nuclei from interacting. But the transformation between those fundamental forces and all of the various cross-sections that show up in nuclear physics is to say that, to put it simply, is very complicated, and we don't always have that transformation. So there's two classes of parameters that we're going to consider, and I will loosely call them fundamental parameters and astrophysical parameters. One more caveat before we give the result, and that is that in physics, we often like to talk about dimensionless quantities. That way we can compare them more easily. So when we talk about the electromagnetic force, you would think the electromagnetic force is determined by the charge on the electron. That's what this E stands for. But instead of actually talking about E itself, we divide by fundamental constants like the speed of light and Planck's constant to define a dimensionless version of that strength. And that's called the fine structure constant. And in our universe, this fine structure constant alpha famously has the value of 1 over 137. Now, you can do the same thing for gravity. You put the gravitational constant in, you have to use a mass like the mass of the proton and your same fundamental constants, and you get a new structure constant, which fundamentally represents the strength of gravity. We can do the same thing for the other forces as well, and I'll show you their values in a moment. But the other point I'd like to make is that in our universe, there's this weird hierarchy, namely that the difference between the strength of gravity and the strength of electromagnetism is about a factor of 10 to the 36. So if you just sit down at your desk and write a 1 with 36 zeros behind it, you'll get an understanding of just how enormous that parameter is. So having said that, what parameters are we going to vary? Again, this is not a definitive list. This is what the analysis that I'm going to describe actually considered. And since this is a short talk, only 7 hours, I understand. It's hard to do jokes online, right? But since this is a limited talk, we're not going to get through all of these parameters today. So what are we going to consider? Well, the fundamental parameters are this. We have the 4 forces, so we have 4 strengths. The strength of the strong force in these dimensionless units is 10. The strength of the electromagnetic force is 1 over 137, which will round to 10 to the minus 2 for this slide. The weak force is somewhat weaker at 10 to the minus 5, and the gravitational force is a whole lot weaker at 10 to the minus 36. We also will consider the mass of the electron, but the mass of the electron is actually usually codified in terms of its ratio to the proton mass, which has this value in our universe, and we'll consider the masses of the up and down quarks, which are the quarks that make up protons and neutrons. Now, if we switch gears over to the astrophysical realm, the relevant cosmological parameters are shown here. We'll come back to these, but let me define them here. Q is the fluctuation amplitude. When the universe was young, it produced little tiny fluctuations in the density field, and these little tiny density fluctuations, which we see in the micro background, grow into galaxies and the structures we see today. In our universe, they started small with an amplitude of only 1 part in 10 to the 5. So that's one of the fundamental parameters. Eta is the amount of stuff in the universe in the form of baryons. It's just a measure of the amount of protons and neutrons that are contained in our universe. It's this crazy number of 6 times 10 to the minus 10 because the way we do the counting is we count the number of protons versus the number of photons. And there's a lot of photons in the universe, so this is a small number. But this is the number in our universe. Because there's not only baryons, there's dark matter, there's a corresponding parameter that tells you how much dark matter there is. There's about 6 times more mass in dark matter than in baryons, and that's why this number is 6 times this one. There's also the cosmological constant, and then there's a nuclear constant, which we will vary, which is a combination of the strong and weak and electromagnetic forces that sets the nuclear action rates in stars like the sun. And you'll see how that plays out once we get a little bit further. So the way you should imagine that you have is imagine that you're designing a universe. So you get your space-time, and you get to choose which parameters has which value. So what you get basically is a dashboard that looks like this. For each of the 12 things that I just told you about, you get a dial, strength of the four forces, the masses of the particles, the cosmological parameters, the nuclear parameter, and stars. And for each one of these, you can imagine turning it up and turning it down. You can make gravity stronger, you can make the electromagnetic force weaker, and so on and so on. So what we'd ultimately like to do is we would ultimately like to redo all of physics and astrophysics with all of the possible values of all of these parameters. Now you can see right away that's kind of a big exercise. It's a big enterprise, and we won't get all the way through it in this morning's lecture, but nonetheless we can try. So what I want to get, or have you come away with at the end of the lecture, is an understanding of what range of values for each of these 12 parameters, which range of values will allow for a workable universe. Now, there's another point we have to put on the table. What do I mean by a workable universe? Again, we have a problem in that what we really want to know with about a workable universe is one that supports life. The problem is we actually don't have a fundamental theory of what it takes to make life. We don't have an understanding of biology at the same level that we have of physics. Mostly, that's not a diss on biology, it's actually more complicated. Physics is easy by comparison. So instead of doing life, what I will use as a proxy is the formation of structure. So I will call a universe to be successful if it can make stars and planets and galaxies, and it can live for a long time. Then I will assume, if that's all good, that life can somehow arise in one form or another. But to be honest, we don't actually know what that takes. So I'm going to spend most of today's lecture, since doing this full parameter space would take literally forever, I'm going to spend most of the rest of the lecture talking about stars, because stars are easy to understand. They're certainly vital for life, and everything else that we do can sort of follow from that lead. So the first question we'll ask is, what values of the four forces of nature, the strengths of the four forces of nature, will allow for stars to work? Now, before I go through this little exercise, you should all think in your minds, well, how big a range is it? Can I vary the gravity by a factor of 2 and still have a working star? Or is it a factor of 2 million? Can I vary the electric force by a factor of 2? Or if I make it 1% stronger, does everything go to hell? We have to do the calculation. So fortunately, I'm not going to make you see the calculation, but let me just tell you what we did. What I built is a semi-analytical model of stars, and it has some simplifications in it. So everything I'm about to show you in terms of stellar structure results from the analytic model are only good at the 10 or 20% level. That's okay, because I want to vary these forces by factors of 10, million, and a billion. So I'm not too worried about 10%, but let me just emphasize that we are making some approximations. The biggest approximation I'm going to make, well, there's two big approximations I'm going to make. One is that we're going to consider one and only one nuclear burning species. So, and only one nuclear reaction at a time. So in the sun, protons get fused into helium. So if I were doing the analog reaction, I would be doing just that. I wouldn't be doing the rest of the nuclear reactions that happen. I could do them separately and later, but I'm only doing one at a time. And the other thing is this. It turns out there's four forces of nature: gravity, electromagnetism, the strong force, and the weak force. But what matters in stars is not the strong force and the weak force separately, but rather what matters is the cross-section for the production of helium. That cross-section is a complicated composite function of the strong force and the weak force. So instead of starting at the fundamental level, what I will do is I will consider gravity as a force, the electromagnetic force as a force, and instead of the strong and weak force, I'll just use a parameter C, which is a composite parameter that represents how much nuclear physics changes, in particular, how much the cross-section for protons fusing into helium changes from star to star. So that allows me to have a parameter space, and I can ask the question, how much can I vary each of these parameters and still have a working star? And here's the answer. If you keep the nuclear constants the same as in our universe, you get the solid curve. And what I'm showing you is the change or the ratio of the electric force in the other universe to our universe on a log scale, and the ratio of the gravitational force to that in our universe on a log scale. So what this means is that if the 0, 0 point is the star where we are, this plane corresponds to making the electric force 10 to the 10 times stronger, 10 to the 10 times weaker. And in gravity, I'm doing the same thing. I'm making it 10 to the 10 times stronger up here and 10 to the 10 times weaker up here. The allowed parameter space where stars work is underneath this solid curve. So you see that I can make gravity about 10,000 times stronger and 1 billion times weaker, and we're all good. I can make the electric force about 100 times stronger and 100 times weaker, and stars still function. But if I go outside those boundaries, then stars no longer work. If I make the electric force too strong, then that shuts down nuclear fusion. If I make the electric force too weak, then all the nuclear fusion happens at once and I get a bomb instead of a star. If I make gravity too strong, then the smallest possible mass star becomes larger than the largest possible star, and I don't have any stars anymore. But I can make gravity basically as weak as I want. I just get bigger and fluffier stars, and everything still works. Now, if I don't keep the nuclear constants the same, and I take this cross-section composite parameter C that I told you about, and I vary it, I get the other two curves on this slide. I vary, if I make C larger, I get a larger parameter space, and I move up to this dashed curve. If I make C smaller, I get a smaller parameter space as marked by the dotted curve. So the effect of the nuclear constant is simply to move this parameter space up and down in this diagram. So this is all well and good. It says that there's actually quite a wide range of parameters in fundamental force space that allows for working stars. But if you think about the problem for a moment, you might say, well, that's all well and good, but maybe I want my stars to have certain properties, okay? So suppose you want the stars to be hot. In particular, you want the stars to be hot enough to drive chemical reactions because that's what life needs. Another way of saying it is you want the habitable zone of the star to lie outside the star. Otherwise, you don't have a habitable planet. The other thing you might want is you might want the stars to live long enough, because we don't actually know how long it takes for life to develop, but in this astrobiology business, a lot of people use 1 billion years as a benchmark. So you might want your stars to live for the equivalent of 1 billion years. Now, why do I say the equivalent of 1 billion years? Well, what we're doing in this exercise is we're changing the laws of physics. In particular, we're changing the fine structure constant alpha. We're changing the electric force. So if we change the fine structure constant alpha, we change atomic structure. So we change the energy levels in the atom, which means we're changing how hot you have to be in order to drive a chemical reaction. And we're changing the time scale at which the electrons go round and round, which sets the time scale of the atom. So what I want to do is I want to require that my stars live long enough where they don't have to live for 1 billion years, but they have to live for the equivalent of 1 billion years, which turns out to be 10 to the 33 atomic clock oscillations. And I also want the energy levels to be comparable to those in our universe when scaled with the different value of alpha. So long story short, if I vary those, I get this diagram. In other words, the solid curve is what I showed you before. That's the region of parameter space that allows for working stars. If I want my stars to be hot enough to drive chemical reactions, I have to be to the left of the blue line. Now, it turns out that the blue line depends exponentially on the value of alpha, so I only need to consider really one value. For the lifetime, I consider 3 values: the moral equivalent of 1 billion years, 10 billion years, and 1/10 of a billion years, and you can kind of see how the constraint varies. So again, if I require my stars to be hot, I have to be to the left of the blue line. If I require my stars to be long-lived, I have to be below the red lines. And that narrows down my parameter space a little bit. Now, you can put on additional constraints. Suppose you require that planets are big enough to hold onto their atmospheres small enough to be non-degenerate. You want the planets to be big enough to be complex so you can support a biosphere. You want the planets to be smaller than their stars so orbits behave the same way. And most importantly, you want stars to be smaller than their host galaxies so you can actually make them readily. If you put all of these constraints on that same diagram, the bottom line you get is shown here. And the allowed parameter space that survives is shown as the dashed region here. And all of those additional constraints I just rattled off actually don't do much, which is why I rattled them off rapidly. And the only thing that matters is that we cut off a corner parameter space here because I want the galaxies to be bigger than stars. So the allowed surviving parameter space in this plane is shown as this dash curve, which has a couple of orders of magnitude up and down in alpha and a much larger range of possible variation in gravity. So far, we have shown that we have this very large parameter space where stars exist, where they're long-lived, where they're hot so they can drive chemical reactions, where the planets are big enough to retain atmospheres, but the planets can still be small enough to not be degenerate, so they have surfaces. The planets are smaller than their stars, the planets are big enough to have a complex biosphere, and the galaxies are big enough that they can cool and produce stars, okay? So we still have a lot of parameter space if this is all that you ask for, okay? Now it turns out that in considering fine-tuning issues in stars, there's 3 additional processes that people care about. And these are a little bit more subtle and a little bit more complicated, but we're gonna nonetheless dive into them. And they're called the triple alpha process and the case of stable diprotons or unstable deuterium. And we'll consider these each in order. So what is the triple alpha process? Well, here's the deal. Everything we talked about so far in the realm of working stars has just required the stars to be successful at being hot and long-lived and undergoing nuclear fusion. So they're providing an energy source to the universe. And they're doing so by turning protons into helium, or at least that's the analog in our universe. But another thing that you might want if you want life is you might want the carbon nucleus to be produced. At least here on Earth, life is carbon-based, and in almost everywhere except for a few science fiction movies, that's the case. So we might want the stars to also produce carbon. Now, there's a famous problem in producing carbon. So what is carbon? Carbon is a nucleus that has 12 things in it, 12 protons, 12 neutrons. Helium is a nucleus that has 4 things in it, 2 protons, 2 neutrons. So you can really, to a remarkable approximation, think of the carbon nucleus as 3 helium nuclei glued together. Okay. And that's sort of a natural way to do it, both in terms of the way nuclear structure works, because nucleons like to live in groups of 4, like in the helium nucleus. And also what stars do is they make 4 protons into helium. So you have all these helium nuclei that are readily produced by stars to make larger elements. But here's the deal. It's easier to put 2 things together than 3. So the natural way to make carbon would be to glue 2 helium nuclei together to make beryllium-8, and then glue a 3rd one on to make carbon. The problem is that in our universe, beryllium-8 is unstable. It's unstable with a half-life of 10 to the minus 16 seconds, give or take, which is kind of short. So at first, there was a big puzzle of how you possibly could make carbon at all. And then it was realized that it's actually not so hard. What happens is that the helium nuclei will make beryllium-8 even though it's unstable. Because it's unstable, it will decay. But if you keep making it, at any given time, you'll have a little bit around that hasn't got around to decaying. Just like when you juggle balls, they all fall, but if you keep throwing them up, they'll stay in the air for a while before they fall down. So what stars do is they juggle their helium nuclei to make beryllium-8, and then they have this small standing population of beryllium-8, which can interact with additional helium nuclei to make carbon, and we're good. But there's a problem. The reaction rate to make the carbon from the beryllium-8 is too slow to account for all the carbon that we have. So there's a second complication, And that second complication is that the cross-section is enhanced by something called a resonance. A resonance is just an excited state of the nucleus, but the problem is it has to be at a very particular energy in order to get the amount of carbon that we see in our universe today. So the question then becomes, how much can you vary that resonance level and still get carbon? Now, to do this calculation, instead of using the simple model that I described earlier for stellar structure, we're going to use a big state-of-the-art computer code and rewire it to consider these new nuclear reactions. So whereas the previous thing you could do on the blackboard, this is a code that takes an hour just to download all the lines of it. So it's a big thing. I'm not going to make you suffer through all the descriptions, but what we can do is we can take this carbon producing algorithm and we can vary the resonance level. So what I'm showing you are the yields of various elements as a function of the change in this resonance level. So in our universe, you don't change it at all, you get 0. If you take a whole collection of stars with different masses and calculate how much carbon you get out of them, and then average over the mass distribution, you get the blue line. So in our universe, carbon gives you about this much, which is 1/10 of a solar mass per star for big stars that make carbon. So that's a lot of carbon. And that's what gives us the carbon in our universe, so that turns out to be the right answer. But you see, as I make the resonance level bigger, the amount of carbon I get goes down. And once it gets down to 400 or 500 keV in these units, I make too little carbon and I'm out of business. If I make the resonance level go the other way, I get more carbon, so that's presumably not a problem. But if I make the resonance level too small on this side, then the reaction doesn't work anymore. So there's sort of a finite range over which you can have proper carbon production. And that range is about 800 keV. That's a unit of energy, that's a range of energy, but we don't know what that means, right? Is that big or is that small? Well, we need a little bit more information. So the bottom line is that there are two things to compare this to. We have this range of 800 keV. Resonances in carbon are spaced every 3 MeV, which means 4 times that. So just randomly, if you have a range of 800 keV, you have a 1 in 4 chance of being near enough a resonance to get carbon to work. So your chances of this working are 1 in 4. Now, it's up to you to decide whether 1 in 4 is good odds or bad odds, but it's reasonable odds. But here's the thing. If you change nuclear physics, loosely speaking, so that you're changing resonance levels by 800 keV, you're also changing energy levels of other nuclei. And the beryllium-8 nucleus only fails to be stable by 92 keV. And the important lesson is this. 800 is bigger than 92. It's easier for nuclear physics to change in such a way as to make beryllium-8 stable than it is to make nuclear physics change so much that you can't produce carbon in stars anymore. And if you can make beryllium-8 stable, then you don't need the triple alpha process at all. Then stars would just do the logical thing. They would fuse their protons into helium, their helium into beryllium-8. The beryllium-8 would be stable. You could fuse it later into carbon in the same star, or you could just spew it all over the universe and put it into carbon later in a different star. So just to verify that you can do this, we took the same stellar evolution code and put in stable beryllium-8, and we can calculate what's called a main sequence. This is just the stars you get, their luminosity versus temperature for varying reaction rates for the beryllium-producing reaction. And it basically looks a lot like the carbon-producing main sequences in our universe. Another thing you can do is just watch the time evolution of a star as it burns protons into helium, helium into beryllium-8, and then beryllium-8 into carbon at the end. So you can make it such that stars can do all of this just like we said. So that's the fine-tuning problem from the triple alpha process which has to do with the production of carbon. And you see that it's not so bad. You have a 1 in 4 chance of being near a resonance already, and it's easier to have stable beryllium-8 than to compromise carbon production. The two other fine-tuning problems in stars are this. In our universe, deuterium is stable, and diprotons are unstable. So if you make the strong force weaker, then deuterium is no longer bound. And if deuterium is no longer bound, then the first step in producing heavy or larger nuclei is problematic, because the way you make a helium nucleus is not to make it all at once, but first 2 protons make deuterium, and then the deuterium eats another proton to make helium-3, and then eats the 4th proton to make helium-4. Along the way, 2 of those protons have to get turned into neutrons, which is what the weak force does. But if you don't have the stable deuterium, the question is, how can you actually make anything go beyond the first step? Well, there's 4 solutions to this problem. The first thing to keep in mind is that if you don't have any nuclear action, stars will still generate a lot of energy. They'll do so just by gravitationally contracting. So what I'm showing you here is the evolution of stars with different masses in the same HR diagram where I plot the luminosity and the temperature. So what you see is that stars form, and then they will have a long period of time when they have a nearly constant luminosity, which is relatively large, even brighter than the sun, and then they will cool down. So just from gravitational contraction alone, you can get plenty of energy, and you can do so for this amount of time. The largest amount of time that you can get gravitational contraction to give you significant amounts of energy is measured in billions of years. So that's a little bit shorter than stars in our universe, but it might be enough. Now, if you have this gravitational contraction and you have big enough stars, what happens in the long run is this. They eventually contract. The smallest stars become degenerate and approach constant density and decreasing temperature. But the big stars get hotter and denser and denser and hotter and hotter and denser until they blow up. Now, under these explosive conditions, you can jump over the deuterium bottleneck, and it's energetically advantageous to form larger things like helium. So these explosive nucleosynthesis events can produce some heavy elements, like where heavy means helium. But once you have some helium, you can produce bigger things later, like carbon. And that leads us to the 4th solution, namely the CNO cycle. CNO stands for carbon, nitrogen, and oxygen. So it turns out there's another way to make helium that doesn't require deuterium. If you have a carbon nucleus, it can eat a proton and become nitrogen. It then beta decays back into carbon-13, which eats another proton to become nitrogen-14. It eats another proton to become oxygen-15, which beta decays to become nitrogen-15, which eats another proton. You nominally think this would become oxygen-16, but it usually breaks apart into carbon, giving you the helium nucleus that you had, giving you a helium nucleus, but you have the carbon back. So you started with a carbon, and you end up with a carbon and a helium nucleus. No deuterium involved. So it turns out that if you have a universe with just a little bit of carbon, you can get stars to burn through the CNO cycle only. So this is the main sequence again, calculated with that same stellar evolution code, using only the CNO cycle. Now, it's not surprising that if you have enough carbon, this would work, because the sun in our universe generates half of its energy through this process. What's surprising is that I can make the abundance of carbon, which is 10 to the minus 2 in these units in our universe. That's called the metallicity. But I can go from 10 to the minus 2 to 10 to the minus 14. And I still have a wide range of stars that's got a bigger luminosity range from 10 to the minus 1 to 10,000, and a temperature range from of order of 10,000. So I can still have viable stars with only a tiny amount of metals. And yet there's another way that stars can deal with the absence of deuterium. Just like in the triple alpha case, even though deuterium's unstable, stars will still make it. It's just that it will decay. So inside a star, protons will interact to make deuterium. If that deuterium can interact with another proton before it decays, it can make helium-3, which is stable, and then you can bootstrap your way up to heavy element production. There's a complication in this, namely that the reaction rate's a little bit slow, but that's actually okay because when the deuterium decays, it decays usually not back into the first two protons, but into a proton and a neutron. And then the neutron will interact almost immediately, and that will let this process go. So if you include this process as well, before we had these main sequences from CNO, the CNO cycle, we have these main sequences from this triple nucleon process. And this is given for different half-lives of the deuterium. 1 EV corresponds to 10 to the minus 16 seconds, which is the same number we met earlier for beryllium. And these are successively shorter half-lives. So 10 to the minus 16, 10 to the minus 17, 10 to the minus 18, 10 to the minus 19. It turns out you can even get a little bit of stars going if you make it all the way up to 10 to the minus 21 seconds, which is almost a little bit longer than the light crossing time of the deuterium nucleus. Now the main sequence lifetimes for these stars are a little bit short. So if you had a universe that only operated through the triple nucleon process, the first generation of stars would only live for as much as a fraction of a billion years. But those stars would then make carbon, and then the subsequent generation of stars operating through the CNO cycle could last for trillions of years. So if you had a universe with unstable deuterium, you would still have stars, you would still have generation of energy, you would still have generation of heavy nuclei, but the process would be slightly different. Now let's go the other direction and look at stars that have stable diprotons. Well, in this case, the problem is that if you have stable diprotons, then you can make nuclear reactions go with the strong force, and you don't need the weak force. And the strong force is stronger than the weak force. Now that all makes sense, but what's a little counterintuitive is that it makes the cross-section for nuclear reactions enormously larger by a factor of about 10 to the 16 to 10 to the 17. And you might think that that larger cross-section would be a problem, but that's effectively making the value of C that we met before larger by a factor of 10 to the 18. But if you make C larger, you just get a bigger parameter space for which you can have working stars. You can also run the stellar evolution code with this enhanced reaction rate. And what you see is that the main sequence in our universe, shown in blue, becomes the main sequence in that universe, shown in red. So the stars become redder. The range in luminosity is about the same, from about 1,000,000 times that of the sun to 1,000th of the sun. But the mass range is a little bit larger. So any given star at any given mass gets a little bit brighter and lives a little bit less long, but the allowed mass range grows, and those two effects almost compensate. So in both a universe with stable diprotons and in our universe, the longest lived stars live for trillions of years, thousands of times longer than the current age of the universe, which is presumably long enough to have life develop. So once again, we see that having stable diprotons is not really a problem. So the bottom line is this. We have gone through quite a lot of stellar physics in the last half hour, and we've seen that no matter what you do, stars tend to be robust. So stars are very robust, not only in being able to generate energy and living for a long time, but if you shut down one pathway for making large nuclei, the stars can figure out or have the possibility to produce heavy nuclei through other processes. they're very robust in that regard. And what that means is that it's really hard for a universe to die by not being able to have stars operate. So the stellar structure part of our fine-tuning exercise is very robust. Said another way, universes are very robust to changes in physics because stars will find a way. So let's go in the other direction. We don't have that much time left, but I want to give you a brief tour of the variations of the other parameters. So let's first deal with the parameter Q. Q is the amplitude of density fluctuations produced in the early universe. We see these density fluctuations imprinted in the microwave background, and we've had several Saturday Morning Physics talks about the microwave background. And famously, the amplitude of these fluctuations is about 1 part in 10 to the 5. So the red spots are hot, they're a little bit hotter and a little bit denser compared to the background, but only at the 1 part in 10 to the 5 level. The blue spots are cooler and less dense, but again, at only 1 part in 10 to the 5 level. But these tiny fluctuations grow into networks of large-scale structure. This is a numerical simulation of the dark matter part of it. And at the interstices of these little filaments, we get galaxy clusters, which grow into the clusters that we see. So the point is this. These fluctuation amplitudes, which are 10 to the minus 5 in our universe, are the starting point for galaxy formation. Now, the question is, how much can you vary this and still have a working universe? The claim is that if you make the fluctuation amplitude smaller, then the galaxies stay so rarefied that they never cool down, and you can't get galaxies to form, or at least not by the present epoch. So you can only make this amplitude about 10 times smaller. The other argument is that if you make this fluctuation amplitude larger, then you form galaxies more readily. You form them sooner, which is not a problem. But if you form the galaxies sooner, they form when the universe is denser, and then the galaxies themselves will be denser. So the question before you then is, how dense can you make a galaxy and still have it be habitable? Now, what can go wrong? Well, two things can go wrong. If you make a galaxy too dense, then the stars are closer together and they whiz by each other, and eventually they'll be so dense that they will strip planets from their stars, and Earth will no longer stay in orbit. So that would be a problem. You also produce so much energy that the night sky can get so hot that you'll boil away the water on any planets. So let's see how bad that is. Well, the answer depends on what mass of galaxy you make. So here I'm showing you the fraction of the galaxy that's not too dense as a function of this Q parameter. Remember, we're here at 10 to the minus 5. And if I have a big galaxy, they're actually not as dense. So almost all of it remains habitable. If I have a little galaxy, they're a little denser. So when I get to a Q of 10 to the minus 2, only 5% or so of the galaxy is habitable. But you still got 5% of the real estate left. So you're never that dense. There's a similar plot we can make for radiation. But here's the cool thing. Suppose I have a sweet spot where I make the density fluctuation amplitude about 1 part in 1,000 instead of 1 part in 10 to the 5. Then I'll have galaxies that are denser. It turns out they'll be about 1 million times denser. In the center, it will be too hot and dense for planets to be happy and habitable. On the outside, it will be cold and dark, just like in our galaxy, and everything will be the same. But there's an intermediate zone. There's an intermediate zone where the night sky is just as bright as our day sky. So think about what that means. If there's a zone where the night sky, all the light from the background stars, gives us about the same amount of light we get from the sun, then every planet will be habitable, no matter where it is. Now, I guess that's not quite true if they're really close to their stars, so they could be too hot, but all the galaxies that are Earth or cooler will be habitable. And if you do the accounting, the interesting thing is that if you engineer a universe with denser galaxies at the right density, there can be so many planets living in this zone here that it can have more habitable planets than our own. So you can actually design a universe with galaxies that have more habitable planets. You can make a universe more habitable. Let's talk briefly about Big Bang nucleosynthesis. Here, the worry is that in our universe, during the first 3 minutes of time, protons get together and make deuterium, lithium, and helium during this early phase called Big Bang nucleosynthesis. The worry is that if you change the parameters of physics too much, then all of the protons will be processed into helium, and we won't have any protons left. And we need protons left because protons are hydrogen, and hydrogen is an important component of water, and we think water is an important component of life. So if you were to have Big Bang nucleosynthesis be too too efficient rather, then you would have no more protons and no hydrogen and no water. So just to show you how that works, what we're going to vary here is the content, the baryonic content of the universe, that's the number of protons and neutrons, and the strength of gravity. So our universe lives here where the star is, where we have our gravity and our value of protons and neutrons. If I go to weaker gravity and less stuff in the universe, I get less nuclear processing and everything stays protons, which isn't a problem. As I go to stronger gravity and more things in the universe, more and more of the universe gets processed into helium. And in this upper corner, I only have 10% of the universe left in the form of protons. So I have less protons and less opportunity to make water. But you see that to get to this upper corner, I have to make the universe have 1,000 times more protons and neutrons in it and 1,000,000 times stronger gravity. So I have to change the parameters of physics quite enormously, and I still have 10% of the protons left. It turns out that if you play this game, it's really hard to kill the universe with Big Bang nucleosynthesis. It's really hard to make all of the things get processed into helium. You always have protons left over. So what about the cosmological constant? Here we have a different kind of problem. Remember the cosmological constant, which you've also heard many Saturday Morning Physics talks about. What it does is it makes the universe accelerate. And here the worry is that the galaxies are forming. We talked about the parameter Q that sets their initial conditions. But once the universe starts accelerating, it shuts down galaxy formation. So if you made the cosmological constant bigger than the value in our universe, the worry is you could shut down structure formation before it completes, and we wouldn't have any galaxies. So the question becomes, how much can you make the cosmological constant bigger and still have galaxies? And the answer depends on the fluctuation amplitude Q that we just talked about. So in our universe, we live at the star where we have our value of Q and our value of the cosmological constant. If I keep Q fixed, I can only make the cosmological constant a couple hundred times bigger before the universe can't make galaxies. But if I make Q larger, like this 10 to the minus 3 value that I liked before, then I can make the cosmological constant hundreds of millions of times bigger. And that's what's shown in this red line. But I have another choice. I can also make the universe have more protons and neutrons. So if I make the universe have more things in it, I can make the cosmological constant even bigger. If you turn all the knobs to the one side, you can make the cosmological constant something like 10 to the 20 times larger than the value in our universe. You could also make it 10 to the 20 times smaller, because nothing bad happens if you make the cosmological constant smaller. So there's a very, very wide range of the cosmological constant that works. Now, for those of you who remember the previous talks about dark energy, even if I make the value 10 to the 20 times bigger, that's still a lot smaller than the predicted value. So there's still a cosmological constant problem, but there's not a fine-tuning problem. And to wrap up, let's go back to the fundamental particle physics parameters that we met at the beginning of the talk. So if I look at what range of the alpha-beta plane is allowed, it looks like this. Let me remind you what alpha and beta are. Alpha is the strength of the electromagnetic force, and beta is basically the mass of the electron, but it's the mass ratio of the electron to the proton. The allowed space is shown here. you see it has several factors of 10 in each direction. So if I make alpha too big, stars shut down and nuclei will fly apart. In order to get stars to work, I have to be up above this triangle, and I can't have the electron be too massive compared to the proton, otherwise atomic structure will be different. So the allowed range is only several factors of 10 in this little window here. I can do the same thing for the electromagnetic force versus the strong force. And again, I get another little square that's several orders of magnitude across. Again, I can't make alpha too big, otherwise nuclei will fly apart and stars don't work. I can't make alpha too small, otherwise stars will blow up. I can't make the strong force too small, otherwise nuclei will fly apart. But I also can't make it too big, otherwise nuclei will become relativistic. But again, you have a window of several orders of magnitude. The most restrictive constraint is from the quark masses, which is shown in this diagram. Here, I am plotting the mass of the up quark and the mass of the down quark, and the biggest constraint is given by these red lines. If you make the quark masses go in this direction, so you make a heavier up quark or a lighter down quark, then it's easier to turn protons into neutrons. And if you do that too much, then if you have a hydrogen atom, the electron and the proton in the hydrogen atom can combine to make a neutron, and you no longer have a stable hydrogen atom. If you go the other direction, you're safe for quite a while. So the most constraining constraint in all the things that we've looked at is this one here. Changing the quark masses too much is the problem. So let me just wrap up now. It'll take me a few minutes to wrap up. But I gave you this whirlwind tour of how much we can vary the various constants and still have a workable, habitable universe. All of those results are kind of summarized in this slide. So let me just tell you what I'm showing you here. For each of the parameters, the ones we met at the beginning, we have the quark masses, the electron to proton ratio, mass ratio, the strength of the four constants, and the astrophysical parameters, Q, the amount of baryons, the amount of dark matter, the cosmological constant. And what I'm showing you here is the number of decades by which I can vary things. That's the number of powers of 10. So like for the first one, the up quark has a range of about 3 powers of 10, a factor of 1,000. Gravity has a range of about 10 powers of 10, a factor of 10 billion. The weak force can be 1,000,000 times stronger, and it can be as weak as it wants and nothing bad. Well, things are different, but no catastrophic things happen. The fine structure constant can be about 2 orders of magnitude bigger and 2 orders of magnitude smaller, and so on. But the point is that for each of these parameters, there's a range in decades, the numbers of factors of 10 that you can vary. And for almost all of them, it's several factors of 10, 6 factors of 10, 4 factors of 10, 3 factors of 10. This whole enterprise was labeled from the beginning as a fine-tuning calculation. If you actually want to tune a radio, you have to specify the frequency in your receiver to about 1% accuracy, because that's how often or how finely the radio stations are spaced. It's a little different for AM and FM, but the number of decades that you can that you need to tune a radio is 0.0043 for AM, and even more precisely for FM. If you compare this number of decades with these numbers of decades, the conclusion that you draw is that it's actually a lot harder to tune a radio than to tune a universe. In other words, it takes us to our bottom line. The fine-tuning of the universe is not as extreme as certain previous treatments would lead you to believe. And what I mean by that is there's a wide range of parameters, many orders of magnitude for most parameters, that will allow for working universes, where again, working universes correspond to those that produce structure, like galaxies and stars and planets. The other thing that you should come away with this discussion understanding is that there are many different channels and pathways by which astrophysics can produce structure and can produce nuclei. we've seen, especially in the case of stars, stars can operate in a whole bunch of different ways. So if you shut down one nuclear processing channel, often another will become important and can work instead. The other sort of overarching conclusion that one could draw is that our universe is not necessarily the best of all possible universes. In other words, I think we can do better. If you were designing a universe from scratch, you could make a more logical universe. So one thing that would be logical is to have larger Q for two reasons. One, it's more natural when you actually try to produce or calculate what value of Q inflationary theory should give, for example. But also, it gives you more leeway to make structure, and it gives you the possibility of having dense galaxies where the night sky is as bright as our day sky, and you can make galaxies with more habitable planets than in our universe. Another way you could make the universe more logical is to have beryllium-8 be stable, because if you look at our universe and you say, well, what are the most common elements? Hydrogen, okay, but there's helium, carbon, oxygen, then there's neon, magnesium, silicon. All of those common elements are basically alpha elements. That means they're helium nuclei glued together with 4, 12, 16, 20, 24, 28, 32, you get the idea. Conspicuously missing is beryllium-8, which has 2 alpha particles glued together. So a logical universe would have stable beryllium-8, then stellar structure could make carbon without triple alpha, and everything would be logical. And it's not that hard to do. And you could imagine that you could make a better universe by lowering the cosmological constant value even more. That would give you more opportunities to make structure. You would get bigger, larger, bigger, badder cosmological structures, and so on. So there's lots of ways you could actually improve upon our universe if you wanted to. Now, just to end, let me just thank my collaborators. This work that I described here was done with 2 postdocs, Evan Groves and Alex Howe, who were here and have now moved on to other places. 2 undergraduates, Lillian Wong and Kate Koppas, who are now both in grad school at Stanford and Maryland. And then Tony Block, who's the chair of the math department. So everything I talked about today was done in collaboration with some set of these people, and it's written in terms of these papers here if you want to look them up. So at this point, I will stop the lecture and I will take questions.
Okay, great. Thank you so much, Fred, for that fascinating lecture and the speculation that goes into that. Ladies and gentlemen, what I did not mention about Fred is that he has also, for many, many years, been a devoted organizer and host of Saturday Morning Physics. And I've worked with him on that in recent years as well. So that's been great. So I want to remind you that this is the question and answer period, and encourage you to submit your questions still and during the next 30 minutes to physics@umich.edu. I also wanted to note that we've had quite a number of viewers today, about 600 at one point. So that's really remarkable. And we're very pleased and grateful for you tuning in to Saturday Morning Physics. So let's go to the questions. Fred, the first question is a very basic question in the sense that it asks a question that's really at the heart of what you're doing, I think. And it comes in several parts, so I'm going to give them to you one part at a time. And the first part is, basically, how does time play a role in this? Is time fundamental? Or does it have a variety of possible properties, such as the direction of time?
Question. So let me just start from the beginning. The kinds of calculations that I presented in this lecture today assume that some kind of general relativity is operational. And what I mean by that is that you have to have some kind of theory where you have a space and a time and a space-time to describe an expanding universe, because the expanding universe is sort of the arena upon which all these different processes play out. Now, within that, you can change the, well, within the scope of what we talked about, you can change the strength of gravity. You can change the content of the universe, the amount of matter, the amount of dark matter, the amount of cosmological constant. So there are different flavors of general relativity that you can play with, but they're all fundamentally incorporated into a framework which is some version of general relativity. And I have not gone beyond that. And what that means is I can't actually answer your question beyond that framework. Now, one of the other questions that's related to what you asked is, can you vary the number of dimensions? So if I have a space-time, I can, in principle, do it with the 3 large space dimensions and the 1 time dimension of our universe. Or I could imagine constructing a theory with 2 time dimensions or 11 space dimensions and that kind of thing. So although I didn't talk about it in the lecture, one can do that. And what you find is that you're only allowed 1 time dimension, and you're only allowed 3 and only 3 space dimensions. Otherwise, things are unstable and things don't work. So maybe you could go to the next part of your question.
Oh, yeah. So it's really in your model specifically, and you may have answered this actually, does time, are there properties of time that have a place? And I guess the real, I'm going to interpret a little bit and talk again about the direction, the direction of time or the arrow of time.
Well, I guess everything that we talked about sort of implicitly assumes that there's an arrow of time which is forward, and you can think of it in sort of 2 different ways. One is that since we have this expanding space-time, which is the arena upon which the universe works, the size of the universe at any moment is in fact a measure of the time. So there's sort of a 1-to-1 correspondence between the size of the universe at any time and the actual value of the time. That correspondence becomes tighter if you have a homogeneous isotropic universe like we do in our universe, and you probably do in many other successful universes. The other thing that gives us an arrow of time is the second law of thermodynamics, namely that entropy increases. And some people have tried to relate the fact that entropy is increasing to giving time an arrow. I've sort of not, I mean, nothing that we really talked about today directly addresses those. So I've sort of implicitly assumed that time just follows the expansion of the universe, and then everything else sort of takes care of itself. These are important fundamental questions. They're just not really in the arena that we talked about today.
Yeah. So I have another one that's not in the arena that is related to time, and it is admittedly a bit egocentric. So let's go back earlier in the universe than the nucleosynthesis that you talked about, and I may ask more about that in a minute, to the actual producing more matter than antimatter, which is sometimes called baryogenesis. So it does involve necessarily time reversal violation or CP violation.
Yes, that's correct.
So
yes.
If you could comment on how much wiggle room there is in that, that actually would have led to a universe with an asymmetry of matter and antimatter, more matter than antimatter.
Well, I guess I think what you're getting at is that in order for the universe to develop an asymmetry of matter over antimatter, which means to have some baryons in it, then you need 3 things. You need to, first of all, have baryon number conservation. And second, you have to have CP violation, as you talked about. And third, you have to be out of equilibrium. It's possible to construct a theory that doesn't have those elements. And then in that case, the universe would not have any baryons, and we would sort of be done from the beginning. So I guess I've implicitly assumed that we do have some kind of baryogenesis. However, you can assume that you're going to have some parts of those, and you can imagine universes with different baryonic contents. So over the course of this lecture, we considered cases where you have more baryons and fewer baryons. And as long as you do have some baryons, the success of the universe isn't hypersensitive to the exact value. In other words, you can have twice as many baryons, and nucleosynthesis still doesn't produce that many helium atoms, and we still have protons left, and so on.
Okay, great. Thank you. So we still have time, so to speak. So I'm gonna a different question related to time is several years ago it was postulated that the fine structure constant may have changed over time. What are people thinking about this, and how might that have an impact on your conclusions?
Well, it's possible that these constants of nature, all of them, especially the strengths of the forces, are actually time variable. People have also considered theories where the gravitational constant is time variable. What we find when we do the experiments is that any possible time variation of the constants are small. The numbers I remember that the change in the electromagnetic constant, alpha, over the age of the universe is less than about 1 part in 10 to the 5. Now, it's possible that there's actually a variation at that level, but it's no more than that. And the data are sort of inconclusive. So either it's constant or it's varying by less than that value. We also know that gravity is more or less constant. We put a time scale on the time rate of change of the gravitational constant. And we know that its time rate of change, or its equivalent time scale, 1 over that value, is more than thousands of times longer than the current age of the universe. So we know that for our universe, the time variations are small effects. And what that means in the present context is if you're only varying the constants of nature by those small amounts and over those large amounts of time, then that won't affect the habitability because the universe is more robust than that. But it's certainly true that if you were to consider enormous time variations, much faster time variations, you would get to a point where you would render the universe uninhabitable anymore. I don't know that anyone's actually done the calculation that you're asking for, so that's something that one could do in the future.
Okay, great. We have a few questions on multiverse idea, and one of them I'll read. You mentioned the multiverse as one possible explanation for why fine-tuning appears to be so special. Physicist Sabine Hossenfelder says that speculating about parallel universes is not science but philosophy. Just because mathematics allows it, does it mean that it is science? I guess is the way I summarize this question.
Okay, well, there's about 4 or 5 questions in there, so let me try to pick them apart. First, I'd like to make the following distinction. When we talk about multiverses and parallel universes, there's at least two classes of things that people mean, and they're different. So let me make that distinction. What I was talking about in this lecture was that our universe is a region of space-time, and it is born somehow at the Big Bang, and it expands, and it goes through this expanding trajectory, which leads to our present-day universe. So we have an expanding space-time. The other universes that I was talking about are other regions of space-time. There's a second way to consider other universes. If you do interpretations of quantum mechanics, there's something called the many worlds interpretation of quantum mechanics, where each time a quantum system makes a measurement or is measured, then it has to make a decision, and the universe splits into all the possible measurement realities. That leads to a different kind of a set of what are sometimes called parallel universes, which is a different collection of universes. So I just want to make clear that when I'm talking about the multiverse in this context, I'm talking about the first sense of that, not the second sense of that. Since lots of us and lots of the audience probably watch lots of science fiction, these two concepts are actually both included and muddled in very many science fiction stories. So you've probably seen something like it. Now then, let us consider just the case that I was considering, namely other regions of space-time. Then the questioner brought up a very important point. Is this science? So it's certainly true that if we have an expanding space-time, which we can describe mathematically with general relativity, it's certainly mathematically allowed for there to be another region of space-time. But then the question is it science? Well, here my answer to that would be that we're right at the border of science. And here's why. Let me draw a parallel to you. The problem that you're, well, let me back up for a moment. The problem that you're seeing is that in order for something to be science, you want it to be experimentally verified, right? And in the strictest sense, if you can't do an experiment, then you can't do science. Okay, well, that's fine. But let's ask a simpler question. When we do stars, you've probably heard me and other folks say that in 6-7 billion years, the sun will turn into a red giant, exhaust its nuclear fuel, expand and eat Venus and maybe eat Earth. Now, no one's ever going to do that experiment. No one's ever going to be around 7 billion years from now to watch the sun turn into a red giant. But yet we say that with a straight face, and no one ever beats us up saying, well, that's not really science because we're not going to be here in 7 billion years. Now let's ask the question, why? Well, the reason is that we actually understand the equations of stellar structure, and we know how it works, and we can verify them in the sun in its present day structure. We can also use that same theory, the same set of equations, and calculate how red giants evolve. And even though we can't look at our sun becoming a red giant in 7 billion years, we can look at other red giants in the sky and get experimental confirmation of that, and so on. So what we would like is for us to understand the fundamental theory of quantum gravity that leads to the launch of the universes, the fundamental theory that leads to inflation, which leads to the acceleration of universes. And we would like to experimentally verify those pieces of physics in our universe. If we could do that at the same level that we understand stars, then we could with confidence say, even though I can't measure the launch of another universe, I can verify all the pieces of the theory in our universe, so I have some confidence that these other things will happen even if I can't do the experiment. In the same way, I have a lot of confidence the sun will in fact turn into a red giant, even though I can't do that experiment either. Now, because you're not doing the experiment directly, this argument I'm giving you is very indirect, we are playing around with or playing around at the boundary of science. So then that leads to another question. Well, is it science? Is it not science? I would say that that's in some sense the wrong question. We're clearly at the boundary of science, but the real question to ask is not whether it's officially science or officially not, but is it useful? Does it actually teach us anything? And one of the reasons why I spend as much time on this topic as I have, and the reason why I'm interested in it, is that it does teach us things. It teaches us how our universe works. As I said at the beginning of this lecture, if you imagine this set of laws of physics with all these knobs, and you turn the knobs to the extreme so that you break the theory and you break the universe and you make it so it doesn't work, you learn what it is that what it takes for our universe to work. In the same way, if you want to like test your car, you take it out on the highway and you slam on the accelerator and you see how fast it goes. You take it to the limit, and that will tell you something about how your car works. So we're trying to do that with our theories of the universe here. We're trying to take it to the limit. And one of the goals is not to hold forth about other universes. Although that's fun, the real goal is to understand our universe. And I think we do that by doing this exercise.
Okay, so I would say that you're a theorist nominally, I'm an experimentalist nominally, but in a sense, you do experiments. You have this fundamental theory that you work with, and then you turn, it's a computer experiment.
Yes, we do. Well, there's two kinds of experiments.
Right. So, but I do think it remains in the realm of science in the sense that you're doing science and postulating and outcomes and using the scientific method for one thing, and you're using the fundamental theories of physics to do these calculations, and then allowing yourself to change a relatively.
No, that's certainly true, and we are following the scientific method. It's only that the end of the scientific method, where you're doing the experimental confirmation, falsification, it becomes more indirect. But that's actually always true. The further you go from your everyday experience, the more indirect all of your experiments become. One of the wonderful things about physics is that we can do experiments under conditions that are pretty far removed from our everyday experience. Like in your laboratory, Tim, you look at atoms, which are pretty small. We don't see those with our eyes. And then the high energy physicists look at things even smaller in their accelerators. So we've gotten pretty far away from our everyday experience in our experiments. This is taking it even further, which makes it even harder and even less secure, but it's part of the same enterprise.
Right. And just to conclude that, though, you would concede that if there were a parallel universe, we wouldn't be able to know about it.
Again, I want to make the distinction between a parallel universe and another member of the multiverse. The parallel universe is a concept of many-body quantum mechanics, which by definition you can't see. The other universes I'm talking about here are causally disconnected from our region of space-time, and the fact that they're causally disconnected means you can't do an experiment there. So the answer is yes, but I just want to be clear what that meant. So
we also have a couple of questions that are related to I guess I would put it this way: there are about 10 or 12 knobs that you can turn, and it's really about what it's like turning them all simultaneously, as opposed to one or a few, which is the way you presented it to us. So the question is, can one multiply all the various probabilities together and get an overall probability distribution for the whole big picture, where all the constraints are satisfied simultaneously?
Well, the answer is that
you can make stars or people.
Yeah, no, you would love to do that. So what you would love to do is to put an overall probability of getting our universe. Now here's the issue, and I phrased things very carefully. I showed you planes of parameters that work, and I was careful to say things like I can make alpha 100 times stronger, 100 times weaker. I can make gravity 10,000 times stronger, 1 billion times weaker. I didn't mention probability. What we can do with our calculations with current understanding is we can see what ranges of the parameters allow the universe to work. But in order to answer the probability question, we need to know more. In addition to knowing the ranges that work, we need to know the probability that you will get each value. In other words, there might be some reason why it might be that, for example, gravity could have any value that's distributed between some minimum value and some maximum value. But it also might be distributed uniformly. It might be distributed logarithmically. It might be distributed according to some Gaussian that's centered on our value. It might be distributed according to some Gaussian that's not centered on our value. The problem with doing the probabilities is that we don't know what probability distribution to use. And the answer you will get for a probability will depend very sensitively on what probability distribution you use. So the short answer is that we don't know enough about the underlying probabilities to answer the question. We would sincerely love to know those probabilities, and then we would love to do that calculation, but we're not able to at the moment.
Okay, so another question takes us to the habitable zones, I guess, in the universe and planets and near stars. And the comment is this, for you to expound on. The macro analysis and analyses are great, but the living conditions could be much more complicated.
Oh, well, that's certainly true. What we've been able to do is put down basic conditions for what it takes to have stars, what it takes to have a galaxy that's apparently habitable, what it takes to have planets with the right properties. If you actually want life to happen, you'll certainly need more things. But I would just draw the analogy, draw the analogy to what we're doing in our universe. In our universe, we know that we have some life because we're here. And we know that we have a variety of stars and a variety of planets and a variety of galaxies. So I'm making, I think, a big assumption. I'm assuming that if you have a different universe that can produce the galaxies and stars and planets in abundance with analogous, not exactly the same, but analogous properties to those astrophysical entities in our universe, I'm assuming that life will also work. There may be something fundamental to getting life to work that we don't know about, in which case you could imagine universes that are alive in the sense of having stars, but not alive in the sense of they might not have life. unfortunately, like I said at the beginning of the lecture, we don't have a fundamental theory of life. Biology is more complicated than stars. We have a set of stellar structure equations that I can write down and I even know how to solve. I would love to have the equivalent set of equations to tell me how an ant works, like a bug ant or a beetle, but we don't, right? If I did that, I would like hang up this call and like start writing a paper, because that would be fundamentally huge.
Great. Another question related to entropy, which is that there's some entropy at the early universe. It started in a state of very low entropy, the question says, which means improbable. So what if that got tweaked? If the entropy, sort of amount of entropy.
Well, you could imagine tweaking the entropy in a couple of different ways. The one measure of the entropy that we have in our universe is codified in the relationship between the amount of baryons versus the amount of photons. Remember the parameter eta that I defined at the beginning of the lecture, which has a value of 6 × 10⁻⁻⁻, some tiny value. The fact that that's tiny means that we have a high entropy, a relatively high entropy to the universe. Now, entropy has a huge range of possible values. So you could imagine starting the universe in an even lower entropy state or a higher entropy state than it is. It's hard to quantify exactly what you mean by that, but I think the short answer is that you have quite a wide range of possible entropies that will still allow the universe to evolve.
Okay. And we have time for one or two more questions. So this question talks about two interesting things. One is Drake's equation and the other is Fermi's paradox. So the question is, how is what you're doing different from a Drake's equation calculation?
Well, first of all, what Drake's equation does is it tries to calculate the number of habitable civil or technological civilizations in the galaxy, and it says it's going to be the number of planets times the fraction that are habitable times the fraction that develop life times the fraction that develop technology, and so on. So that's just a way of saying these are the things I want to know in order to see how many civilizations there are. What I'm doing here is in some sense similar in that I'm considering different universes and asking the question, what does it take for them to work? But I'm doing something different. Instead of just saying, well, I'm going to assume a probability that we're going to have technology arise. What I'm doing instead is assuming or finding the range of values of particular constants, like the strength of gravity, the fine structure constant. I'm finding the ranges that work. So the exercise is a little bit different. What was the second part of the question?
Oh, well, it was, if you have a brief answer, it was, what are your thoughts about Fermi's paradox?
Oh, well, then Fermi's paradox is the question of if there's that many civilizations, then where are they? That doesn't really play a role in today's lecture because the other universes are causally disconnected. So any visitors from other universes would, by definition, not be able to be here. My answer, well, there's lots of answers to Fermi's paradox, and I don't have any particular insight, but I do have one solution to Fermi's paradox that most people don't think about. So I can give you that, and it might just be fun to talk about, and that's the following. What I'm sort of assuming in this exercise is that once you have the laws of physics in place that are good enough, whatever that means, then life will arise. So suppose that we understand life at the same level that we understand stars, and suppose further that when we understand life at that level, what we find is that if you seed life on any planet, it's always going to evolve sort of the same way. And I mean the same way statistically, not the same way specifically. The same way weather is the same from year to year, even though the weather is not the same from day to day. So suppose that's the answer. And that means that if aliens were to come to another planet and institute life, the life that would be there and develop there would be qualitatively the same as the life that's already there. And if that's the case, then the aliens just wouldn't bother to come because there would be no point. And this could actually work or be the solution if it's easier to figure out biology than to figure out space travel. Because if you understand biology at the fundamental level, and the answer is what I described, so two big ifs, and that's easier than figuring out how to go from star to star, then any civilization that develops space travel will have already figured out biology and then not need to go. So that's kind of people hate that idea as a solution to the Fermi paradox, but I like to bring it up because it makes people think.
All right, well, we still have a lot to think about. Thank you very much, Professor Fred Adams, for the lecture and for this discussion. And thank you to all of the viewers and everyone who sent us questions. We didn't quite get to all of them in the time we have, but it's been a wonderful discussion. And thank you very much. We want to remind you of next week's Saturday Morning Physics, which is by Professor Julie Young from the University of Michigan Naval Architecture and Marine Engineering Department. So we'll see you next week, and thanks a lot. Bye-bye.
Thank you all.